Hello there. Welcome to another problem session. This is more of a concept session than problem session. So we have a what is called alternating current circuit. So AC stands for alternating current, meaning the direction of the current goes back and forth. So the current direction at one time would be this way. Say T1, some other time, if I look at the same point, it will be, current will be that way. So this is current depends on the time, the direction of the current. So clearly current is changing. So if you look at the magnetic field through this area, magnetic flux will be changing. Hence, it is a dynamic circuit. So even if you just have a plain wire, you'll have a self-inductance, a resistance, and a capacitance in the circuit. Okay. Of course, you can build a circuit which is can be. This is my AC source, and I can put a resistor here which is way more than all the other resistance anywhere else. So that with the resistor, I can put a capacitor here, and I can put an inductor here, and so inductance of this thing dominates self-inductance from there. So self-inductance of this is the only one we would take into account, and same for capacitance here. But even if for a circuit, you are going to have resistance, capacitance, and inductance. Okay, so if your voltage changing with frequency f, so we call this kind of thing as an AC voltage source. Now there is also a source you can construct and buy, is AC current source, where current through here is maintained this with this function. So you have an AC voltage source or AC current source. So this one fluctuates current between plus I0 and minus I0 with time, and this is 0. Here between A and B, the voltage fluctuates. But if you look at the voltage A and B, between A and B, that depends on what else is connected. Okay, so here the voltage voltage is going like this, and in between V0 and minus V0, and this is 0 with time t, and this is one whole period, and this one whole period is 1 over frequency, right? Okay, so but the current that's going through here, that depends on time, and it's not going to have this form. We are going to find that I of t will have, it will have some magnitude, and it's going to be cosine, and it's going to be 2 pi ft plus there's going to be some phase come that actually here if I write down the phase of the voltage, if I write like that, this is equal to 0. Phase of the voltage through the source is 0, but over here it's going to be phi I, and phi I will maybe 0 sometimes, depends on what RL and CR values are. So we have to figure out what phi of I formula is. Okay, now this is the case only if t is much less than this damping time. So because you have R and L, there's a damping part to it. So if you look at the time t, so if this is L over R, this is complicated behavior in this time. Let's look at the current I. But out here, current over here, current is actually sinusoidal. Is with the same frequency, and so this time is 1 over f. Now this sinusoidal current is in a steady behavior in this time domain, and this is called steady state, and this is state, and this here is a transient. So when you switch here, it can be very complicated, and if let it settle down, that's why you want circuit to settle down. You warm up, so-called warm up. You turn the circuit on and let it warm up. Warm up means you've gone beyond this time, and you are in this steady state behavior. Okay. So I'm going to set up the equation that helps me solve this problem. All right. Okay. So the equation here will be obviously Faraday law, right? And that, if you remember, it's minus E dot dl. So dl is a path we choose. So I'm going to go in that direction. So this is closed path. So dl is like that along the path, and that should be equal to d dt of flux change through this area of the loop, b dot n hat dA. And if I go like this, the n hat is in that direction. If we go like this, yeah, so n hat is in that direction. Use the right hand rule. Well, in a circuit where only current is changing, so this is when only I of t and not some b is also changing. So this whole thing is because of the changing, when on changing, when just this is happening, this whole thing can be written as L di dt. So this equation becomes, if I go from here, I have a first I from here to here, say A to B, C, D. So A to B, I get V0 cosine omega t for this guy. And then if I go B to C, I have a minus Ri, and C to D is minus 1 over C I t prime dt prime. So we look at this plate where the current, say at this instant t, the current is going this way. So this is the positive plate, we say. This is Q of t. So that's the definition, which is my positive plate, which is negative plate. Positive plate is the plate at which current is going in. So this is all left side, and the right side is just here as a placeholder for what happens on the right side. So right side of the Faraday law, it just tells me this will be L di dt. So I can just rearrange it. So we have a L di dt plus 1 over C di t prime. T prime is a dummy variable. And this integrate, so just keep the top part, plus Ri is equal to V0 cosine omega t. Well, we can actually if you like, we can just take a derivative of the whole thing. There's a couple of different ways, so we can write it one way, and another way is like this. Take another derivative that makes this guy come out. So this is L d square I dt square plus 1 over C it plus R di dt because minus omega v0 sine omega t. So solve this equation. Or another way to do it is just call this guy q of t. Then I don't take this becomes L d square q dt square plus 1 over c q plus r dq dt equals v0 cosine omega t. So here you have v0 cosine omega t, here you have a minus omega v0 sine omega t. But both of the both way you can just solve it. It's more or less the same equation. And when you solve this, if you solve this for q of t, for t much greater than L over R, if you solve this, you're gonna get a q of t will be some kind of a some q0 cosine omega t plus phi for the property q. It's going to look like this, and then I can take a time derivative. So I of t will simply be equal to minus omega q0 sine omega t plus phi q. Now I can absorb this minus sign inside there and convert this sine to cosine. So first put a omega q0. So if you have a sine theta, if you got a minus here, okay, then this is same as sine theta plus pi. So let's see, if it's got sine theta cosine pi, that will be minus sine theta, and the other one will be 0. So this is just going to be equal to sine, or you can even write the cosine. So this will be like a cosine theta plus pi over 2. So cosine theta cosine pi, that will give 0, minus sine theta sine pi over 2, that's going to be that. So just I'm going to write this as a omega q0 cosine, this whole thing omega t plus whatever I find phi q plus pi over 2. So this will be phi I, if this is all 0, if this is positive, if positive, okay, then that will be I 0. If not positive, then this minus can be absorbed further inside here by adjusting the phase. Okay, so this is that path, and this path you can just go directly, just solve it. Okay, let's do this direct path. Okay, so I'm going to erase some of this, and so actually a good way to solve this problem is using a complex numbers or complex variables, but I'm going to try to avoid that. We're going to use some sense here, like if I have a cosine omega t plus b sine omega t, if that equal to 0, then that will mean a has to be 0 and b has to be 0, because these functions are independent. You can show several ways. Say if I has to be 0 for all t, so this you can say when cosine omega t is 0, sin omega t is 1, and when sin omega t is 0, this is 1. So that's how you can get both of these equations. So that is going to be a method for solution. So what we're going to do is let I equals to some I0. I'm going to write cosine omega t I0 c plus I0 sine omega t. So I'm going to have a mixture of that. From there you can see that if this was I0 cosine omega t plus phi I, then I0 will simply be equal to square root of those guys, I0c square plus I0s square, right? And then you can from there phi I will be it will be related to this guy and this guy, and so we're gonna find by doing this. Okay, phi will be obtained by just looking at I0 cosine phi I is equal to I0c, and I0 sine phi I equal to I0s, and you can take a tangent on phi. It's just going to be I0s over I0c. So I can get those if I can find these guys, right? So I'm going to just plug these guys in here, and in here, and see what I get. Left side, right side we already know. So I get a I di dt. Let me work this out and then I'll show you. Okay, so I went ahead and substituted these guys in here, and hopefully it's come out right. Okay, so there is a sine omega t here, and sine omega t, sine omega t, sine omega t. So these guys will give me one equation, and these guys will turn out to equal to 0. So from these guys, I'm just gonna get minus L omega square plus 1 over c times I0c plus omega r I0s equal to 0. And from these guys I'm going to get minus L omega square plus 1 over c I0s minus omega r I0c, that's equal to minus omega v0. So I can solve for these guys and then just plug in here and get the answer, right? So now it's just basically two equations, two unknowns. So the unknowns here are just these guys. These guys are the unknowns. It's the same, and these guys are the unknowns, right? So you can see many different strategies. This is just a, let's call this guy A. So this A I0c. Let's call this guy B I0s equal to 0, and so this is minus B I0c plus A I0s equal to 0. So this is writing not 0, minus omega v0. So already I see that if I multiply this by B and multiply this by A, I can get rid of A I0c, right? So B square plus A square I0s is minus omega A v0. So I0s I0s is just minus omega a v0 over b square plus a square. And of course, put in here gives me I0c equals minus b over a times this stuff, minus omega a v0 over b square plus a square. So there's a lot of algebra, but a lot of physics is problem is a lot of algebra, and you have to kind of go through it. So I'm going to leave that as an exercise. So I am leaving as an exercise to complete these steps, complete to get I, 0 and phi of I. Okay, so this is one of the steps that's needed to actually address questions like how much power is consuming, whether there going to be resonance of the power, there's the resonance of the current, what's the resonance frequency. You will find out that this thing, combination, plays a very important role. We're just calling A here, and there's a special frequency. Omega is 1 over omega squared equals to 1 over LC, meaning omega equals to 1 over square root of LC. This frequency is at which most power can be delivered to the circuit. Okay, and this is called resonance frequency. So this you'll find it. This is called resonance frequency. Resonance frequency of power, that power can be delivered. Okay, I'm going to stop here. This is a lot of algebra, and I hope things were clear to you conceptually. If you have, go ahead, please subscribe if you haven't subscribed already. This helps get the channel out. And if you like this kind of explanations, please hit the like button. Definitely check out this book. This book is some of the earlier versions of what you will see in some places. Okay, bye.